For our third and final conservation of energy example, example number 3, we're going to look at something that has multiple parts. So here we have a spring of known spring constant, 600 newtons per meter, and we're told it's been compressed 80 centimeters. We've placed a 7 kilogram mass in front of that spring, and when we fire this spring, we want to first know what will the velocity of the ball be at A, how fast we'll be traveling at A, and how fast we'll be traveling at location B once it's kind of moved up that hill and is rolling along the top of that 2-meter high hill. All right, so if we want to take a look at this, we're going to approach this in much the same way we've been approaching it the entire time. We just have to identify different points based on what we're looking for. So to find the velocity at A, I think it makes sense to use point 1, which is prior to being fired, and point 2, which is when the ball reaches location A. So we have my conservation of energy equation. The next step is going to be to kind of cross out whatever quantities of energy I know I don't even have. So prior to firing the spring, I only have elastic potential energy in the spring. After it's been fired, I'll only have kinetic energy because the spring will have released its energy. There's no height, so all the energy will be in the kinetic form. I can simplify that expression by saying the elastic potential energy will become the kinetic energy, and I could substitute in the equations for those two forms of energy. I then just have to plug in whatever values are known. So I can plug in the spring constant and the displacement of the spring from its resting length in meters, so 0.80 instead of 80. And I'm going to set the equal to 1/2 the mass times the velocity squared. If we do our algebra correctly, we should find that the velocity that the ball must be traveling at A in order to conserve the energy it was given by the spring should be 7.41 meters per second. In order to solve for the velocity at B, we're going to do a similar approach. At this point, I think for me, I'm going to say going from 1 to 3 is probably going to be easiest for me, but I could also go from 2 to 3. It doesn't matter. The energy is constant throughout. So just understand you could compare point 2 and point 3. I'm going to decide to compare point 1 and point 3. So I'm going to adjust those equations accordingly. So again, still point 1, so there's no gravitational potential or kinetic. In fact, point 1, we only have elastic potential. However, now at point 3, yes, it is rolling, but it's also rolling 2 meters above where originally it started. So it has both potential due to the height, gravitational potential, and kinetic due to its motion. So from point 1 to point 3, it's a little bit different because the elastic potential energy we started with by the time it reaches B will be stored in both the gravitational potential energy due to the height and the kinetic energy because that ball will still be rolling. Now I can substitute in the equation. So 1/2 kx squared equals mgh plus 1/2 mv squared. And I can plug in the values as I did previously. 1/2 k delta x squared equals mgh plus 1/2 mv squared with all the associated values plugged in. If we do our algebra correctly, we should find that by the time this ball reaches the top, it will only be traveling at 3.65 meters per second, which makes sense. That's less than the 7.41 at point A, and we would expect it to be less, because if the ball had 100% of its energy stored in the kinetic form at point A, then 7.41 is really the maximum velocity it's ever going to travel at, assuming something doesn't come in and give it more energy. To move up that hill, it's going to have to give up some of its kinetic energy so it can become potential energy. Therefore, with that lower kinetic energy value at B, we would expect less velocity, which in fact we do find.